Welcome to The Explainer. Today, we're going to go behind the scenes on something pretty much all of us have gone through, but probably never really thought about: the dental x ray.
Yeah, we've all been there, right? Sitting in that chair, you hear that little whirring sound, then that quick flash. But have you ever stopped to think, what is that flash? What happens in that split second? And where does that x ray actually go?
Well, today we're going to follow that hidden journey. It's a wild story, really. It starts with just a spark of energy, and it ends up being a super important diagnosis. And in between, oh, just a whole lot of physics, a bit of geometry, and honestly, some pretty serious detective work. So, yeah, let's dive in. Okay, so first things first, our story doesn't actually start in your mouth. Nope, it begins way back, deep inside that heavy metal arm of the x ray machine. There's a part in there called the tube head, and that's where all the magic, or, the physics really happens. So inside this tube head, the absolute star of the show is a metal called tungsten. This stuff is just incredibly dense, almost as dense as gold, actually, and it's packed with 74 electrons, which you'll see is the key to this whole thing. But it's not just about being dense. Tungsten has this kind of a superpower that makes it perfect for this crazy intense job. And this is its superpower. Just look at that number, over 3,400 degrees Celsius. To put that in perspective, that's more than double the temperature of molten lava. It's insane. That is tungsten's melting point, and it's the highest of any metal on Earth. And that heat resistance is precisely why it's the chosen one. It can take all that crazy energy needed to make an X-ray and not just, vaporize. All right, so we've got our super powerful X-ray beam. Awesome. But making it, that's only half the battle. Now you've got to aim the thing, and with some serious precision. Getting a clear image isn't as simple as point and shoot. Oh no, it's a game of angles, a game of geometry. One of the classic ways they do this is called the bisecting technique. Now, I know, it sounds super technical, but just think of it like this. You've got the angle of the tooth, right? And then you've got the angle of the little sensor they put in your mouth. This technique is all about finding the exact middle point between those two angles and aiming the X-ray beam right at that imaginary line. It's literally about splitting the difference to get an image that's true to life. But here's the catch. This whole technique is super, super sensitive. If you're off by just a tiny bit, you get something called dimensional distortion. That's really just a fancy way of saying the picture gets all warped. And a warped picture, that can lead to a totally wrong diagnosis. For example, check this out. If the angle of the beam is too steep, coming from too high up, you get what's called a foreshortened image. The tooth looks all squashed and stumpy. And the real danger here? An image like this could completely hide a serious problem, like an infection or a tiny fracture that's right at the tip of the root. And then there's the other side of the coin. If the angle is too flat, you get elongation. Now the tooth looks all stretched out, kind of like you're looking at it in a funhouse mirror. And again, a distorted image like this is pretty much useless for a diagnosis. So you can see, it all boils down to precision. Getting that angle just right is everything. Okay, so all the little pictures have been taken, one by one. But now comes the next big challenge, putting them all together. You can end up with a full set of like 18 or even more of these little films, and someone has to arrange them into a perfect, coherent map of the entire mouth. The training manuals for dental professionals have this perfect, simple instruction for this part. It just says, mount like puzzle pieces. And that's exactly what it feels like. Every single little X-ray is one piece of a much bigger picture, and they all have to snap into place just right. And putting them in that mount isn't just about being neat and tidy. It's actually super important for a bunch of reasons. I mean, it stops you from mixing up the left side of the mouth with the right, which would be bad. It protects the films themselves, and it even helps the dentist see better by blocking out extra light. It just makes the whole process way safer and way more accurate. The way they do it is actually a really cool mix of simple clues and some serious anatomy knowledge. It starts with this little raised dot on every film, just to get the basic up and down orientation. But then the real skill comes in. The technician uses their knowledge of anatomical landmarks, like the upward curve of your lower jaw, which has a name, the curve of Spee, to place every single one of those puzzle pieces exactly where it's supposed to go. All right, the puzzle is complete. The map is laid out, and now the real detective work begins. It's time to read the story that's hidden in all those shades of black, white, and gray. So one of the first things a trained eye is looking for are the dark spots. The technical term is radiolucent. Just think of it like this. Darkness means the X-rays just sailed right through that area. And that's usually a red flag. It means something that should be dense, like healthy bone or tooth, has been replaced by something less dense, which could be a sign of an infection, a cyst, or an abscess. And then, of course, they're also looking for the exact opposite radio-opaque areas. These are the bright white spots. And whiteness means the X-rays got blocked, kind of like a big rock in a stream. This points to something that's denser than the tissue around it. Now, that could be something simple, like a filling, or even just a harmless little patch of extra dense bone. So the professional scans the entire set, systematically, tooth by tooth, looking for these little clues. And the clues can be incredibly specific, like a sharp, dark line on the crown of a tooth. That's a classic sign of a fracture. A neat little dark circle right at the tip of a root. That's the textbook sign of a certain type of cyst. Every problem has its own signature, its own telltale sign. So, after all this work, generating the beam, getting the angle right, putting the puzzle together, who makes the final call? Who actually figures out what it all means? This really brings us to the most critical step of the whole journey. It's a really important question because the answer shows you just how much teamwork is involved. This isn't just a one-person show. It really is a team effort. You have the dental hygienist, who's the technical expert, right? They're the ones taking the pictures, making sure they're clear, putting that whole puzzle together. But, and this is the key takeaway, it's the dentist who makes the diagnosis. They're the one who looks at all that evidence and says, okay, here's what's going on, and here's what we're going to do about it. And just like that, the journey's complete, all the way from a spark of superheated tungsten to a critical diagnosis. It's a pretty incredible process when you think about it. And it just goes to show you that behind that simple little flash in the dentist's office, there's a whole world of science and skill and incredible precision. And it kind of makes you wonder, right? If a simple black and white picture of our teeth can tell such a detailed story, what other hidden stories are our bodies just waiting to tell? All right, let's pull back the lead apron on a piece of technology almost all of us have experienced, but let's be honest, very few of us actually understand. The dental X-ray. What is really going on behind that familiar whirring sound? You know the drill. You're sitting back in the chair, they put that heavy vest on you, and then they aim this strange device at your cheek. You hear a quick little beep, and that's it. But what just happened? I mean, what really went on inside that machine in that split second? Well, the secret ingredient is a really special kind of energy called X-radiation. The easiest way to think about it is like a super-powered flashlight. Its light can pass right through soft stuff, like your gums and cheeks, but it gets stopped by the denser things like teeth and bone. And that's what creates that hidden picture of everything going on underneath. Okay, so to really get how we can create an X-ray pretty much on demand, we've got to do a super quick review of the basic building blocks of, well, everything. We're talking matter and energy. It all boils down to the atom. You've got the nucleus in the middle, sure, but for our story today, the absolute star of the show is that tiny particle just zipping around the outside, the electron. Seriously, that little guy is the key player in this whole thing. And here's the tiny, tiny change that makes all the difference. A normal, stable atom is neutral. It's got the same number of protons and electrons, so it's balanced. But if you can hit that atom with enough force to knock one of its electrons clean out of orbit, it's not balanced anymore. It becomes a charged ion. And that process, ionization, is the whole idea behind what we call ionizing radiation. So now that we've got the basic physics down, let's step inside the factory. That tube head the dentist points at your face, it's not just a camera. It's basically a miniature particle accelerator, a highly specialized factory that makes only one product, X-ray photons. So here's the assembly line in action. First, electricity heats up a tiny tungsten filament, which boils off a cloud of electrons. The second you hit that exposure button, a massive voltage difference acts like a giant slingshot. It launches that cloud of electrons across a vacuum tube at nearly half the speed of light, and they just slam into a small tungsten target at the other end. Now, when those electrons hit the target, you'd think the result would be pretty efficient, right? Nope. It's actually shockingly inefficient. A full 99% of all that incredible kinetic energy is instantly converted into nothing but waste heat. Only one tiny, precious percent actually becomes the X-rays we need. That's why the whole thing is bathed in insulating oil, to absorb all that heat. And get this, even that 1% isn't all the same.
It's actually a mix of two different types of radiation, which are created by slightly different atomic collisions. But for the person taking the X-ray, what's way more important is how they can control this beam. So now we've created this incredibly powerful beam of energy. But how do we control it so we get a crystal clear diagnostic image instead of, just a useless fuzzy blob? Let's head over to the control panel and see how the operator dials in the perfect shot. It really just comes down to two main dials. First, you have kilovoltage, or kVp. That controls the quality of the beam. Think of it as its penetrating power, or how hard it hits. Then you have milliamperage, or MA, and that controls the quantity, literally the total number of X-rays being made. It's a classic trade-off, quality versus quantity. Okay, so let's look at the cause and effect here. If you crank up the kVp, the power, the image gets darker. But look what else happens. It actually decreases the contrast, which gives you more shades of gray. Now, if you just turn up the milliamperage, the quantity, the image also gets darker, but the contrast doesn't really change. It's a really delicate balancing act to get it just right. So why would a dentist even want to mess with the contrast? Well, it all depends on what they're looking for. A high contrast image gives you these really sharp, distinct blacks and whites, which is perfect for spotting a cavity. But if you're looking for something more subtle, like bone loss from gum disease, you actually want a low contrast image with lots and lots of shades of gray. The tool has to be tailored for the job. So the perfect beam has been created, it's been aimed, and now it's time for its final incredible journey. We're talking about the milliseconds it takes for it to travel through your jaw. What actually happens when these little packets of energy meet the atoms inside your body? So, every single one of those photons has one of four possible fates. Most of them are going to scatter, and a good chunk will get absorbed. But what we're really interested in is that tiny fraction that manages to pass all the way through without interacting with anything at all. Because believe it or not, those are the ones that actually make the picture. All right, quick quiz. First scenario, an X-ray photon zips right through your cheek, misses every single atom along the way, and hits the sensor on the other side. What do we call that? That is called no interaction. And these photons are the true heroes of the story. They're the ones responsible for creating all the dark parts of the X-ray, the spots that represent soft tissue or empty space that the beam just sailed right through. Okay, next up, what about the most common thing that happens? This is where a photon comes in, collides with an outer shell electron, knocks it loose, and then kind of ricochets off in a new direction with less energy. That one is Compton scatter. It happens the majority of the time, and it's the main reason we have scatter radiation, which isn't great because it can create a sort of fog on the image. So it's the most common interaction, but it doesn't really help us see anything. And last one, what if the photon doesn't scatter at all? What if it makes a direct hit on a really tightly bound inner shell electron and transfers all of its energy, just completely vanishing in the process? That's the photoelectric effect, and it's the other critical interaction we need for a good image. So let's put all these pieces of the puzzle together. When you get right down to it, a dental X-ray is just a shadow map, created by this beautiful little dance between all these different atomic level interactions. So let's recap the big stuff. Dental X-rays are born from a super high-speed collision of electrons into a tiny target. The whole process creates a ton of heat just to make 1% of useful radiation. The person taking the X-ray uses kilovoltage for the beam's power and milliamperage for its intensity. And that final picture? It's really just a detailed shadowgram, painted by the photons that got absorbed and the photons that passed right on through. So the next time you're sitting in that chair and you hear that little whirring sound, you'll know. It's not just a machine, it's a controlled chain reaction of atomic physics all happening in a blink of an eye to help you out. It really makes you wonder, right? What other everyday technology that we take for granted is hiding such incredible physics just under the surface? You know the drill. You're sitting in the dentist chair, they drape that heavy apron over your lap, and you bite down on a little piece of plastic while they aim a machine at your cheek. But what's actually going on in that moment? Well, today, we're diving into the incredible story of the dental X-ray, from a really dangerous discovery to a cornerstone of modern medicine. So let's get into it. First, we'll explore why dentists even need these X-ray superpowers. Then, we'll meet the pioneers who figured this all out, often at a terrible personal cost. After that, we'll break down the nitty-gritty science of how radiation actually affects our bodies. And finally, we'll weigh the risk versus the reward right here in the 21st century dental office. All right, first up, why do we even need these images?
It turns out what your dentist can see with just their eyes is only a tiny, tiny fraction of the real story of your oral health.
And it all comes back to that one question we've all had, right? Why do they step out of the room for something that seems so routine? The answer is all about the power and the historical danger of what that little button unleashes. But first, let's see what that power actually shows us. Think of your dentist as a detective. Seriously, X-rays are their #1 tool for investigating everything that's happening below the surface. They can spot cavities hiding between your teeth, see cysts or even extra teeth buried in your jawbone, and check on how everything's developing long before it becomes a visible problem. Without these pictures, they'd be flying completely blind, and tiny issues could turn into massive problems. So how did we get this incredible tool? Well, the story is pretty amazing. It's full of brilliant discovery, but it's also a serious cautionary tale about the price of progress. It all started way back in 1838 with a simple vacuum tube built by a guy named Heinrich Geissler. Decades later, in 1895, Wilhelm Röntgen was messing around with one of these tubes when he noticed a screen across the room started glowing. He'd stumbled upon a mysterious new ray, he called it the X-ray because he had no idea what it was, and he famously took that spooky image of his wife's hand. And get this, just 1 year later, an American dentist named C. Edmund Kells brought this brand new tech right into the dental office.
Dr. Kells was a true innovator, a real trailblazer. But here's the thing. Nobody knew about the dangers of radiation. Not a clue. So to get a good, clear image, he'd hold the film plates in his patients' mouths with his own fingers, soaking up dose after dose of radiation day in and day out. He was pushing the boundaries of medicine, completely unaware of the invisible damage being done to his body.
And this is the painful price he paid. The very tool he championed was slowly destroying him. The story of Dr. Kells is absolutely tragic, but it's such a crucial part of this history. It forced the entire scientific community to stop and ask a critical question. What was this invisible energy actually doing to us on a cellular level? So, to understand what happened to Dr. Kells and to understand how we stay safe today, we have to shrink down, way, way down to the atomic level. This gets us into the invisible science of what was happening inside his cells. Okay, meet the main villain in our story, the free radical. The easiest way to think of it is like a little agent of chaos. It's an unstable atom with a single, lonely electron. That makes it desperate to be stable again, so it goes on a rampage, stealing an electron from any molecule it bumps into. This sets off a destructive chain reaction inside a cell. So how are these little troublemakers born? It's a pretty simple 3-step process, actually. First, an X-ray photon zips into a cell, and bam, it hits a water molecule. And remember, our cells are mostly water. Second, the energy from that collision knocks an electron right off the water molecule. And third, what's left behind? That's our unstable, electron-hungry free radical. Now, this whole process leads to 2 main theories about how radiation causes damage. You've got the direct theory, which is when an X-ray gets lucky and scores a direct hit on something super important in the cell, like its DNA. But that's pretty rare. What's way more common is the indirect theory. This is where the X-rays create those free radicals from water, and then those free radicals go on to do the damage. So the key thing to remember is that water usually acts as the middleman for most of the damage. Okay, so that was the scary part. I know, but this story doesn't end there. Not even close. The sacrifices of pioneers like Dr. Kells led to a total revolution in safety, which has completely flipped the script on the risk. So how exactly do we stay safe today? Well, it comes down to a handful of brilliant innovations. We have stable X-ray tubes that give a predictable, controlled dose. We've got incredibly fast digital sensors that need just a tiny fraction of the radiation they used in the old days. We use something called collimation to narrow the X-ray beam down to just the size of a postage stamp, so only the target is exposed. And of course, there's that heavy lead apron, which is basically your personal shield. So with all that new technology, what's the actual risk today? Well, the potential risk of a routine dental X-ray causing a fatal cancer is estimated to be about 3 in 1 million. Now, that's an incredibly small number, but what does it really mean in the real world? This is where it all clicks into place. Let's put that risk in perspective. The chance of a fatal outcome from a dental X-ray is about the same as smoking 1.5 cigarettes or riding your bike for 10 miles. It's actually less risky than driving 300 miles in a car.
We take on these kinds of risks every single day, most of the time without even thinking about it.
And that brings us to the ultimate takeaway, the bottom line. It's all about that tiny, managed risk you take for a huge diagnostic reward. Yeah, there's a risk, but it's vanishingly small. The benefit of finding a hidden infection or a cyst or decay before it gets bad, benefits that can save your teeth and maybe even your life, that benefit just vastly outweighs the minimal risk. You know, the story of the dental x-ray isn't just about dentistry. It's a really powerful reminder of this constant balancing act we do between our relentless search for knowledge and our absolute need for safety. It went from a mysterious glowing screen in a lab to a precise diagnostic tool, and it shows our incredible ability to harness powerful forces for good, all while learning from the past to protect our future. Have you ever really thought about a dental x-ray? I mean, how can a piece of plastic that looks totally blank suddenly reveal everything hidden inside your teeth? Well, today we are pulling back the curtain on that little piece of analog magic. We're going to find out how invisible energy gets turned into one of the most important tools in dentistry. So, right off the bat, here's the big question. How do you develop an invisible picture? Think about it. The x-ray is taken, the film comes out of your mouth, and it looks like nothing. It's totally blank. So how in the world do we get from that empty-looking film to a super detailed image of teeth and bone? That's the puzzle we're here to solve. And here's the secret. The picture is already there. You just can't see it yet. It's hiding. The whole process of developing a film is basically a carefully choreographed chemical dance, and its only purpose is to bring that hidden image out into the light. And that invisible picture, it actually has a name. It's called the latent image. Now, this isn't ink, and it's not light. It's literally a pattern of stored energy, captured in the film the exact moment the x-ray zapped through the patient's jaw. Our job is to turn that energy pattern into something we can actually see, and that is where the darkroom comes in.
Okay, but before we can bring this latent image to life, we've got to understand the canvas it's painted on. So, what is a dental x-ray film, really? Let's break it down.
The best way to think about it is like a tiny, high-tech sandwich with 4 layers. Each one has a super important job. You've got a strong film base at the bottom for support. Then there's an adhesive layer to kind of glue everything together. On top of that, you have the absolute star of the show, the film emulsion. We'll talk way more about that in a second. And then finally, there's a thin protective layer on top, just to keep the whole thing from getting scratched. Now listen, every layer is important, but the film emulsion, that is where all the action happens. This is the heart and soul of the film. It's the part that's actually sensitive to the X-ray radiation. So what makes this emulsion so special? Well, it's packed with millions of microscopic silver halide crystals. Just picture them as these teeny, tiny energy sponges. When X-rays hit them, they just soak up and hold on to that energy. The more X-rays that hit a crystal, the more energy it stores. And that pattern of energized and non-energized crystals, that's our invisible latent image. All right, so we've got our film, and it's holding this hidden pattern of energy. Now it's time for the main event, the darkroom dance. This is where chemistry takes the lead and transforms that stored energy into a real, visible, permanent image. Now, inside an automatic processor, this dance follows 5 very specific steps. First, the film takes a dip in the developer, which makes the image appear. Then, a quick rinse stops that process. Next, it goes into the fixer to make the image permanent. After that, a final wash gets rid of any leftover chemicals. And finally, it gets dried, and ta-da, it's ready to view. Every single one of these steps has to be perfect. But let's simplify this. Out of all those steps, it really comes down to 2 key chemicals. Think of the developer as a detective. Its mission is to go in and find only the silver halide crystals that got hit with X-rays. And when it finds them, it turns them into black metallic silver. That's what makes the dark parts of the image appear. Then, right after, the fixer comes in. Think of the fixer as the cleanup crew. Its job is to find all the unexposed crystals, the ones that were protected by bone and teeth, and it just washes them away completely. That leaves the film clear in those spots and makes the whole image stable and permanent. So, the chemical dance is over. A picture has magically appeared out of what looked like nothing. But what are we actually looking at? Let's figure out how to decode this thing. You have to remember, an X-ray isn't really a photograph. It's more like a shadowgraph. It's a map of shadows. The black, white, and gray areas you see are a direct result of how dense the stuff was that the X-rays had to travel through to reach the film. And we use two main terms to read this shadow map. First, you have radiolucent areas. These look dark or black. This happened where X-rays just sailed right through stuff that isn't very dense, like your gums, or unfortunately, a cavity. On the flip side, you have radio-opaque areas. These look light or white. This is where really dense things like tooth enamel or a metal filling stopped the X-rays in their tracks, leaving the film underneath totally untouched. Now, this chemical dance we've been talking about is a really delicate performance. The timing, the temperature of the chemicals, how you handle the film, everything has to be just right. So what happens when somebody misses a step? Let's look at what happens when this beautiful dance goes wrong. You know, in our digital world, we're used to having an undo button. Well, with analog film, there's no such thing. One little mistake can make the whole X-ray completely unreadable. And you know what that means? The patient has to get another dose of radiation to take it all over again. The stakes are pretty high. Okay, time to play detective. Take a look at this film. You can see part of the image, but then there's this perfectly straight, totally clear border on one side. What on earth could cause that? Any ideas? That is a textbook case of developer cutoff. It means the developer chemical level was too low and that edge of the film never got submerged. So our detective, the developer, never even got a chance to work on those crystals. And when the detective doesn't do its job, the cleanup crew, the fixer, just comes in and washes everything away, leaving it completely blank. All right, here's our next case file. Two films went into the machine, but they came out stuck together. And where they were touching, there's this dark, sticky, ugly patch. What happened there? Yep. That's just a classic operator error called overlapped films. Someone fed the second film into the machine way too fast, right on the tail of the first one. When they stick together like that, the chemicals can't get to the film surfaces properly, and you're left with this underdeveloped, sticky mess. Okay, this one is my favorite. It's so weird. The picture of the teeth is pretty clear, but there's this strange geometric pattern, kind of like a tire tread or a waffle iron, stamped across the whole thing. What in the world is going on here? The answer is so cool because it actually teaches us about the film packet itself. This is a reversed film. It means the film was put in the patient's mouth backwards. See, inside every single film packet, there's a thin sheet of lead foil. It's there to absorb extra radiation, but if you put it in backwards, the X-rays have to go through that foil first, and they end up taking a picture of the foil's pattern right onto the film. And finally, we've got chemical contamination. This is what happens if you're not careful in the darkroom. If a drop of developer splashes on the film before it goes into the processor, it starts working early and creates dark spots. The detective got a head start. On the flip side, if a drop of fixer splashes on it, it washes away the crystals before they can even be developed, leaving light or white spots. The cleanup crew showed up way too early and ruined the party. When you see how much can go wrong, it really makes you appreciate a perfect X-ray. It's not just a picture, it's a testament to incredible precision. It's a small victory for a scientific craft that took over 100 years to perfect. And really, that brings us to a final thought. This whole complicated hands-on process, this chemical dance, this used to be the absolute peak of technology. Now, of course, we have digital sensors that give us an image instantly, with way less work and less radiation. It's so much better for everyone. But it does make you wonder, doesn't it? In our huge leap forward in convenience and speed, what have we gained? And what kind of artistry have we maybe lost along the way? Hey there! So, have you ever looked at a dental x-ray and thought, what am I even looking at? You know, just a jumble of black, white, and gray? Well, what if I told you that every single one of those images is actually a story? Yeah, a story packed with clues about what's really going on inside our jaws. And today, we're going to learn exactly how to read it. Okay, let's just dive right in. Take a look at this image. See that spot? Right there, nestled between the roots of those two teeth. Something's definitely going on there. But what is it? What story is this specific X-ray trying to tell us? Stick with me, because by the end of this, you're going to be able to describe exactly what you're seeing with total confidence. For real. All right, but hold on. Before we start solving any mysteries, we've got to lay down some ground rules. Every good detective knows you have to understand the rules of the game first, right? And when it comes to dental images, the biggest rule is knowing the difference between interpreting what you see
and diagnosing it. So, there's a really important line in the sand here. Interpretation? Well, that's all about describing what you see. It's an explanation of the image itself. Think of us as the crime scene investigators, just gathering the clues. And hey, any trained dental professional can do this part. But diagnosis? That's the why. That's identifying the actual disease. And that's the final call for the dentist, and the dentist alone. And honestly, this is absolutely crucial. Our job as these dental detectives is to get really good at using the right language to describe our findings. We're just presenting the evidence, clearly and accurately. We're not the judge and jury delivering the final verdict. That's a super important distinction, both legally and professionally.
Okay, so if we're going to present that evidence, we've got to learn to speak the language, right? Dental radiology has its own lingo, so let's jump in with the two most basic words you absolutely need to know. So everything you see on a dental image boils down to one of two things. It's either radiolucent or radiopaque. Radiolucent, that's the darker black stuff. It's dark because X-rays just pass right through it because it's not very dense. Think of things like soft tissue or a cavity. Now, radiopaque, that's the light or white stuff. It's white because it's super dense, like bone or filling, so it blocks or absorbs the X-rays. Seriously, it's just black and white. That's it. This is tool number 1 in our detective kit.
All right, we've got our basic terms down. Now we need a system. I mean, every great detective has a method, right? A way to make sure no clue gets missed. Having a system like this means we can describe what we see completely and consistently every single time. And our method is super simple. It's just 3 steps. First, we describe its appearance. What does it actually look like? Second, we pinpoint its location. Exactly where is it? And third, we note its size. Appearance, location, size. That's it. That's our framework.
So let's tackle step 1, appearance. We're going to start with the words we use to describe those dark or radiolucent areas. Because trust me, there's a lot more to say than just, hey, look, a dark spot. Okay, so one of the most common things you'll see is something we call unilocular. Let's just break that word down. Uni means one, right? And locular basically means compartment. So a unilocular lesion is just a single, self-contained dark spot, one little compartment of something that's not supposed to be there.
But wait, the clues don't stop there. You've got to look at the border, the edge of the lesion. If it has a corticated border, you'll see this thin, really well-defined white line around it. That's often a good sign, suggesting something that's slow-growing and probably benign. But a non-corticated border that looks fuzzy, kind of poorly defined, that can be a hint that something is a bit more aggressive. It's a bit more of a wild card. Could be benign, could be malignant. See? The edge of the clue tells its own little story.
So what if it's not just one single compartment? Well, then we call it multilocular. Multi for multiple, right? This is a lesion that has a bunch of different chambers, and it often ends up looking a lot like soap bubbles, all clustered together. That soap bubble look can be a sign of a more aggressive type of growth. Okay, so that's the vocabulary for the dark, radiolucent stuff. But what about the light, radiopaque lesions? Yep, they have their own set of descriptive terms, and they can be just as interesting to find. The most basic one is called a focal opacity, and it's pretty much what it sounds like. A focused, well-defined white spot. You can almost think of it as the opposite of a unilocular lesion. Instead of a single dark spot, it's a single bright spot, one little area that's dense enough to block those X-rays. Oh, this next one is super cool. It's called a target lesion, and it looks, well, exactly like a target. You've got this bright, radio-opaque bullseye in the middle, and it's surrounded by a dark, radiolucent halo. That mix of light and dark creates this really unique pattern that just jumps right out at you. Okay, boom. That's appearance. Now, on to step 2, location. Describing where you find something is just as critical as what it looks like. Is it periapical, meaning it's right around the tip of a tooth's root, or maybe it's interradicular, sitting between the roots of 2 teeth next to each other? It could be in an edentulous zone, an area where there are no teeth, or it might be pericoronal, which means it's wrapped around the crown of an impacted tooth. Each of these terms is like giving the clue a precise street address. Okay, people, we've learned the rules of the game, we've learned the lingo, we have our 3-step method. You know what that means? It is time to put it all together. Let's go back to that mystery we started with. Time for the big reveal. Remember this guy, that little dark spot that seemed so mysterious when we first started? It doesn't look so intimidating now, does it? Because now we have the tools.
We have the language to describe exactly what we're seeing. So let's do it. Let's use our three-step system.
All right, let's break this thing down. Step 1, appearance. What do we see? It's a single dark area, right? So that's a unilocular radiolucent lesion. And if you look really close at the edge, see that sharp, thin white line? That means it has corticated borders. Okay, step 2, location. Where is it? It's right between the roots of those two teeth, which makes it interradicular. And finally, step 3, size. For this, we'd simply measure it and write down the dimensions in millimeters. And just like that, it's not a mystery anymore. It's a clear, well-described set of clues ready for the dentist to make the final call. So here's the takeaway. By learning a pretty simple language and following a clear system, you can turn what looks like a confusing mess into a coherent story. The mystery just evaporates, and you're left with solid information. So the real question is, now that you know the language, what clues are you going to be looking for in your next X-ray?
Have you ever sat in the dentist chair, stared at your own X-ray, and just nodded along? You have no clue what you're looking at, but you pretend you do. Well, not anymore. Today, we're going on a decoding mission. We're going to learn the language of that image and understand the story it's telling. Let's get into it.
So you look at a full set of dental X-rays like this one, and yeah, at first glance, it can look pretty intimidating. Kind of like a weird abstract piece of art, right? A whole landscape of shadows and light. But hidden in there is a super detailed story about everything from the tip of your tooth's root to the top of its crown. The real question is, how do we learn to read it? Okay, this right here, this is a Rosetta Stone. It's the key to understanding everything else. And honestly, it's pretty simple. Things that are less dense, like the air in your sinuses, let X-rays pass right through, so they look dark. We call that radiolucent. But things that are really dense, like your tooth enamel or a filling, they block the X-rays and they look bright white. That's radio-opaque. So just remember, dark means less dense, light means more dense. That's it. That's the secret code. Now, before we can start playing detective and spotting problems, we first need to know what normal looks like. So let's take a quick tour of a healthy mouth, find all the major landmarks, and get our bearings. Think of this as our map for the journey ahead. First stop, the upper jaw, which is called the maxilla. And right above your back teeth, you've got these big, hollow, air-filled spaces. These are your maxillary sinuses. They're a huge, totally normal feature on any X-ray of your upper teeth. And since they're filled with air, which, isn't dense at all, they show up as these big, dark areas on the X-ray. It's the perfect example of a radiolucent structure. Sometimes people see this big, dark space and worry it's a problem. But nope, most of the time, it's just your sinuses saying hello. All right, let's head down to the lower jaw, or the mandible. Running right through it is this super important structure called the mandibular canal. You can think of it as a protected tunnel that carries the main nerve and all the blood supply to your lower teeth. On an X-ray, you'll see this canal as a dark band. But if you look really close, you can often spot two very thin, bright white lines running alongside it. That's the dense bone that makes up the walls of the tunnel. Knowing exactly where this is located is absolutely critical for a dentist planning any work on the lower jaw. Now let's zoom way in and look at just one healthy tooth. It's kind of like a layer cake of different densities. That outer layer, the enamel, it's the hardest, densest substance in your entire body, so it shows up as the brightest white. Right under that is the dentin, which is a little less dense, so it looks more like a grayish white. And then, right in the middle, you have the pulp. That's the living nerve and blood vessels. Not dense at all, so it appears as a dark chamber running down the center. Okay, so we have our map. We know what a healthy mouth is supposed to look like. Now, let's see what it looks like when things go wrong. We'll start with the more obvious stuff, trauma. A fracture, it's pretty straightforward, right? It's a break. It can happen in the top part of the tooth, the root, or even the jawbone itself. And it probably won't surprise you to hear that our source material says crown fractures happen most often in the front teeth, while the lower jaw, the mandible, is the jawbone that gets fractured the most. And here's where that first rule we learned comes right back into play. A break creates a tiny bit of space where there used to be solid, dense tooth or bone. And on an X-ray, that little space lets the X-rays pass through, showing up as a sharp, dark line. It's a classic, telltale sign of a fracture. But trauma isn't always about breaking things. Sometimes it's about moving them.
This is called luxation. So, intrusion is when a tooth gets jammed up into the bone. Extrusion is when it gets partially knocked out of the bone. And avulsion? Well, that's the one you really don't want. That's when the tooth gets knocked out completely. The X-ray is key here to help the dentist see what kind of damage has been done to the socket.
But a broken or knocked out tooth is often something you can see pretty clearly. The real magic, the real power of X-rays is finding the problems you can't see, the hidden issues lurking just beneath the surface. This is where the real detective work begins. For example, have you ever heard of tooth resorption? It's kind of wild. It's when the body itself starts to break down and absorb its own tooth structure. If it happens from the inside out, that's called internal resorption, you might see a weird, round, dark spot that looks like it's hollowing out the tooth's center. If it happens on the outside of the root, external resorption, the tip of the root might start to look kind of blunt or even shorter than it should be. Now, a huge amount of this detective work happens in one very specific spot, the very, very tip of the tooth's root. The technical term for that tip is the apex. This is a super common area for infections or inflammation to show up in the bone, and we call those periapical lesions. And what's really fascinating is how the body can react in two totally opposite ways down there. On one hand, you have problems like abscesses or cysts that cause bone loss. They destroy the bone, which creates these dark radiolucent spots on the X-ray. But on the other hand, sometimes the body reacts to a long-term low-grade irritation by building extra bone. It creates a denser area that shows up as a bright white radial pake spot. So the body can either take bone away or add more, and both are huge clues for your dentist. And get this, here's a cool little tidbit from our source material. That bright white spot of extra dense bone, the one called condensing osteitis, is the single most common radio-opaque thing seen around a root tip in adults. It's just the body's way of building a little fortress of bone to deal with irritation. So, we've learned the language, we've toured the landmarks, and we've spotted some trouble. But how does a dentist actually take this single black and white image and come up with a final diagnosis? Well, and this is so important to remember. The X-ray is just one piece of the puzzle. It's not the whole story. As you can see here, the X-ray is the initial clue. But then your dentist adds context by actually looking in your mouth, and they get the backstory from you, your patient history. It's only by combining all those pieces that they can reach the final conclusion, a real diagnosis. And this quote from the source material just sums it all up perfectly. You can't diagnose just from a picture. Sometimes two completely different problems can look almost identical on an X-ray. It really takes a professional's expertise to put all the pieces together and figure out what's truly going on. Look, the goal today was never to turn you into a dentist. It's about making you a more confident, informed patient. Think of your X-ray as a map. And now that you understand the basic language of light and dark, you have the tools to follow along, ask smarter questions, and be a real partner in your own healthcare journey. So, the next time you're sitting in that chair and your dentist puts that image up on the screen, you're not going to just see a confusing jumble of black and white. You're going to see a story. And now you have a much better idea of how to read it. What new details will you be able to spot?
All right, you know the drill, right? You're sitting back in the dentist chair, they throw that heavy lead apron over you, and then they swing this weird cone-shaped machine right up to your jaw. There's a little beep, and poof, it's done.
But have you ever stopped to wonder how that machine just took a picture through you? I mean, how can it see through your skin and bone to get this perfect image of your teeth? It feels like some kind of magic trick, but it's not. It's just pure, amazing physics.
And that's the journey we're going to take today. We are going to follow the life of an X-ray, right from its birth inside an atom, all the way to that final picture that tells your dentist what's going on. So, let's get into it.
Okay, so to get how the picture works, we first need to understand the flash that takes it. And for that, we've got to go inside the machine itself, inside the tube head. You can basically think of it as a super specialized photon gun.
So, inside this glass vacuum tube, you've got two key players. First, there's the cathode. It's got a negative charge, and its only job, its whole purpose, is to supply the ammunition, which in this case is electrons. Then on the other side, you have the anode. It's got a positive charge, and it's the target. Its job? To stop those electrons, dead in their tracks.
So how do we get those electrons from the source to the target? Well, it all starts when a little tungsten filament inside the cathode heats up, like really hot. This heat actually makes a cloud of electrons boil right off the surface. It's a cool process called thermionic emission. And then, the second the dentist hits that button, a massive high-voltage circuit kicks in. Bam! This creates this intense electrical force that just launches that electron cloud across the tube.
And when I say launches, I mean it. These things are moving unbelievably fast. We're talking about going from a dead stop to nearly half the speed of light in a tiny gap that's less than an inch wide. It's insane. And then wham, the electrons just slam into this little tungsten target over in the anode, carrying a ton of kinetic energy.
Okay, but here's the crazy part. For all that incredible speed and energy, the whole process is, well, it's super inefficient. Get this, only 1% of all that energy actually becomes useful X-rays. The other 99%? It's just instantly converted into heat. A lot of heat. That's actually why the target is stuck in a big copper stem, to soak up all that heat and pull it away.
So, out of that violent, super hot collision, kinetic energy from an electron gets transformed into something totally new. A brand new particle is born. This is our hero, our protagonist, the X-ray photon. And now its journey is just getting started.
So what exactly is an X-ray photon? Well, first off, it's not the electron anymore. Think of it as a tiny, weightless packet of pure energy. It has no mass, no electrical charge. It's just this little bundle of pure energy zipping along in a straight line at the speed of light.
And this little photon, it's got some wild properties that make it perfect for what we need. For one, it's totally invisible. It can also pass right through solid stuff. And here's the most important part. It can cause something called ionization. That's basically where it can knock an electron out of another atom it hits. That last one is the key to everything. It's how we get an image, but it's also the reason why radiation exposure has to be so carefully controlled.
Right, so this is the million-dollar question, isn't it? We've got this invisible beam of pure energy flying straight through your cheek. How in the world does that turn into a black and white picture of your tooth?
It all comes down to one word: density. Imagine you're throwing a bunch of tiny balls at your face. As these X-ray photons travel, some of them are going to be stopped and some are going to get through. The soft, less dense stuff, like your gums and cheeks, they don't block many photons. So the photons pass right through and hit the sensor on the other side, and that makes the picture dark. We call that radiolucent. But the really dense stuff, like bone or your super hard tooth enamel or a metal filling, that stuff absorbs or just flat out blocks the photons. Since no photons can get through to the sensor in those spots, they show up as white, and that's what we call radio-opaque.
So really, the image is just a shadow picture, a shadow graph created by all those different densities. But to get a really clear picture that a dentist can actually use, they need to be able to control that X-ray beam with incredible precision.
And this is how they do it. There are basically two main dials they can turn. First is milliamperage, or MA. Think of this as the quantity of X-rays. The more MA, the more photons you're shooting, and the darker the overall picture gets. The other dial is kilovoltage, or kVp. This one controls the quality, how much penetrating power each photon has. Cranking up the kVp gives you more shades of gray in the image, which is perfect for spotting subtle things like early gum disease.
It's not just about the electricity, though. The physical shape of the machine matters a lot, too. For example, having a super tiny focal spot on that target inside the tube, that gives you a much sharper image with less of that fuzzy, blurry edge that dentists call penumbra. And using a longer cone, that part they aim at your face, makes sure the X-ray beams are nice and parallel. That means you get way less magnification and a truer picture of the tooth.
So you see, it's all a balancing act. By perfectly juggling all these things, the quantity of X-rays, their quality, the geometry of the machine, a dentist can turn this invisible beam into a powerful tool. A tool that makes the invisible visible and helps them find problems they'd never see with their own eyes.
No, it's so easy to take this technology for granted, but it's actually the result of more than 100 years of incredible discovery, innovation, and yeah, sometimes real sacrifice.
It all kicked off back in 1895. A guy named Wilhelm Röntgen stumbles upon this mysterious new ray, and because he has no idea what it is, he calls it the X-ray, X for unknown. The amazing thing is, just 1 year later, a dentist in the US, C. Edmund Cales, is already using it on his patients. From there, things just took off. William Coolidge invented the modern X-ray tube we still basically use today in 1913, and then of course, digital imaging completely changed the game in 1987.
But being a pioneer like that, it came with a huge cost. See, back then, nobody, including Kells, had any idea just how dangerous this invisible energy really was. He would actually hold the little film packets in his patients' mouths with his own fingers every day. The result was just tragic. He developed cancer that over time cost him his fingers, then his hand, and eventually his entire arm.
That story, it's a really powerful reminder of just how far we've come. Because we now understand the physics so well, we've been able to take what was once this dangerous, mysterious novelty and turn it into one of the safest, most essential tools in all of modern medicine.
Think about it. We went from a simple cloud of electrons to a detailed map of the inside of our own bodies. The story of the X-ray really shows how learning to control an invisible force can literally change everything. It kind of makes you wonder, right? What other invisible forces are out there that we're just starting to understand today, and how are they going to shape the medicine of tomorrow?
You know the drill. You're sitting in the dentist's chair, they put that heavy apron on your lap, and you have to bite down on that awkward piece of plastic. But have you ever stopped to think about what's actually happening in that split second? Well, today we're going to pull back the curtain on the incredible journey of a dental X-ray, all the way from a single photon to a final diagnosis. It's this wild trip that starts with a tiny, invisible photon, travels right through you, and ends up as this critical piece of information that can literally save your teeth. And our story doesn't start in the dentist office. It starts over a century ago. And this quote, man, it just perfectly captures the spirit of discovery. So back in 1895, a scientist named Wilhelm Röntgen notices this mysterious glow coming from a screen in his lab. He had no clue what these powerful invisible rays were, so he just called them X-rays, X for unknown. Little did he know, his investigation of that unknown would change medicine forever. And you know what? The dental world moved fast. We're talking just weeks after Röntgen's discovery, a German dentist, Dr. Otto Walkhoff, took the first dental X-ray on himself. And get this, the exposure time was a staggering 25 minutes. Can you imagine? These early pioneers risked their own health to push this technology forward, which eventually led to the much, much safer X-ray tube we know today, developed back in 1913.
Okay, so how does that machine on the wall actually create an invisible beam of energy? Well, it all happens inside this part called the tube head. Let's trace the birth of a single X-ray photon, step by step.
Think of it like a four-step dance of physics. First, a current heats up a tiny filament, kind of like in an old light bulb, until it's so hot it starts boiling off a cloud of electrons. That's called thermionic emission. Then, a super high-voltage circuit acts like an electromagnetic cannon, launching these electrons at nearly the speed of light towards a small metal target. And when they slam into that target, bam! That violent collision converts all their speed and energy into a powerful burst of X-ray photons. Now, this is where it gets absolutely wild. For all that amazing physics, the whole process is incredibly inefficient. Just look at this. A staggering 99% of the energy from that collision is just wasted as pure heat. Only a tiny single percent actually becomes the useful X-ray beam we need. It's just a crazy reminder of how much power is being harnessed just to create that 1%. And these are the key players that make it all work. It's really a story of opposites attracting. On the negative side, the cathode. You've got the tungsten filament creating the electrons and a special focusing cup to aim them like a lens. They're all fired across to the positive side, the anode, where they smash into the tungsten target. And that simple-looking copper stem, it has one of the most critical jobs of all. It acts like a giant heat sink, pulling away that massive 99% of heat, so the whole machine doesn't just melt down. But here's the thing. Creating that powerful beam is only half the battle. Capturing an image that's actually useful for diagnosis, that's a true art form. It relies completely on the skill of the person taking the X-ray. Let's see why. The best way to think about a radiograph is to picture it as a super sophisticated shadow map. The X-ray beam is the light source, your teeth and bones are the objects casting the shadow, and the little sensor in your mouth is the wall where the shadow is recorded. And by studying those precise shadows, dentists can see everything that's hiding beneath the surface. But getting that shadow map just right is tricky. The angle of that X-ray machine is absolutely critical. If the angle is too steep, you get what's called foreshortening. The tooth looks comically short. If the angle is too flat, you get elongation, and it looks all stretched out. This shows you exactly why technique matters so much. A distorted image like this could easily hide a tiny fracture or an infection, making the whole X-ray useless. So, once a perfect shadow map is captured, the next step is to decode it. This is where a dentist translates all those black, white, and gray shapes into real, crucial information about your health. To read this map, you really only need to know 2 key words. Anything that shows up dark is called radiolucent. That just means X-rays passed right through it easily. Think soft tissue, nerves, or, and this is the important one, areas of decay. On the flip side, anything that looks white or light gray is radio-opaque. That means it's dense and it blocked or absorbed the X-rays, like your healthy tooth enamel, fillings, and bone. This table is basically the perfect cheat sheet. Healthy, dense stuff like enamel and bone, that's going to be bright white or radiopaque. The soft tissues inside your tooth, radiolucent or dark. But here's the key. Look at pathology. Things like decay and abscesses show up as these dark, radiolucent spots. Why? Because the disease has literally eaten away the dense, healthy tissue that used to be there.
And here is a textbook example. A dental abscess, which is basically an infection at the very tip of a tooth's root, destroys the bone around it. So in an X-ray, it shows up as this distinct dark circle, a radiolucent spot, right where there should be solid, healthy white bone. It's a dead giveaway that lets dentists find these hidden problems deep inside your jaw.
You know, this brings up a really important point. While a trained hygienist or assistant can interpret an image, they can describe what they see, like, hey, there's a dark spot at the tip of this tooth. Only the dentist can legally make a diagnosis. They're the one who can officially say, this is a periapical abscess. It's a critical legal and professional distinction. All right, of course, we can't talk about X-rays without addressing the elephant in the room for a lot of people, radiation. So let's actually look at the real risk versus the incredible reward. So let's put this all in perspective, okay? The amount of radiation you get from a full set of modern digital dental X-rays is roughly the same as you'd get from a short 1 or 2 hour airplane flight. It's also just a tiny fraction of the natural background radiation we all get just from living on planet Earth for a year. Besides, every dental office follows a strict principle called ALARA. It stands for as low as reasonably achievable. They use special filters to block the weak, unnecessary X-rays, a lead collimator to narrow the beam so it only hits the target, and super sensitive digital sensors that need way less radiation than old-school film. Every single one of these things, right down to that lead apron, is designed to keep your exposure as low as humanly possible. So when it all comes down to it, it's pretty clear. The ability to find a serious problem, like an infection or a cyst or even a tumor, long before you ever feel it, well, that benefit is just monumental. And it's weighed against a very minimal, highly controlled risk. So that really brings us to the final question, doesn't it? When you weigh the incredible power of seeing things that are completely hidden from the naked eye against the tiny, controlled risks we've just talked about, what's the verdict? For me, the answer is pretty clear. From Roentgen's mysterious glowing screen all the way back in 1895 to the instant digital images we get today, the dental X-ray is still one of the most powerful tools we have in our arsenal. It's a simple, quick procedure that truly lets us see the invisible and lets us stop small problems before they ever have a chance to become big ones.
Hey everyone, welcome back. You know the drill, right? You're at the dentist, they slide that little plastic thing in your mouth, you hear a beep, and boom, a picture of your teeth pops up on the screen. And most of us, we just assume they're on a hunt for cavities. But today, we're going to peel back the curtain and see what those black and white shadows are really telling us. It's a whole hidden world in there. So that's the big question. What is your dentist actually looking for? You got to think of them as a detective, and that X-ray, that's their #1 clue. They're piecing together a story, the story of an old injury you forgot about, or the body's super quiet response to a problem, or just the subtle changes that happen deep inside a tooth over your entire life.
All right, let's start our journey on the outside and look at how things like external forces, what dentists just call trauma, can really impact not just your teeth, but the bone that holds them in place.
So when we talk about trauma in dentistry, we mean any kind of injury from an outside force. You know, a fall, taking a basketball to the face, any kind of impact. And yeah, you might see a chip on the surface with your own eyes, but the X-ray is absolutely crucial because it tells the rest of the story. It shows that hidden damage to the roots and the jawbone that you would just never ever see otherwise.
It's pretty cool how different kinds of fractures show up. Crown fractures,
the ones you can often see, usually happen right on those front teeth. But root fractures? Oh, those are way trickier. The X-ray beam has to hit the fracture line at the perfect angle just to spot it. And then for the really big impacts, you might get a jaw fracture, which almost always happens in the lower jaw. On a big panoramic X-ray, it shows up as this clear, dark line.
Now, sometimes a tooth isn't actually broken, but it's been knocked out of place. The fancy term for this is luxation, and it's all about displacement. And as you'll see, a tooth can get displaced in a few very different ways.
So this slide really breaks it down nicely. There are 3 main ways a tooth can go. Intrusion is when it gets shoved deeper into the bone. Extrusion is the opposite. It's partially pushed out of the bone. And then there's avulsion, which is the most dramatic one. That's when the tooth is knocked completely, totally out of its socket.
Okay, so that covers all the damage that can happen from the outside. But what about the changes that start from within? Now we're going to go deeper, right inside the tooth itself, to see how it reacts to things like injury, inflammation, or even just the process of aging.
Now this is where things get really weird and interesting. It's a process called resorption, where the tooth's own structure just starts to dissolve. And it can happen from 2 directions. You've got external resorption, which starts on the outside of the root. It can make the root tip look kind of blunted or shorter. Then you have internal resorption, which starts from the inside and basically hollows out the tooth. It's almost like the tooth is being eaten away, either from the outside in or the inside out.
So here's another thing that happens on the inside. It's called pulpal sclerosis. The best way to think about it is that the pulp chamber, the living center of the tooth, it just slowly starts to shrink. It's like the tooth is building a thicker wall on the inside as we get older. It's not really a problem, but it's a super clear sign of aging that you can see right on the X-ray.
And then you've got the more extreme version of that, with pulpal obliteration. That pulp chamber makes so much extra dentin that it literally looks like it's been filled in completely. You look at the X-ray and the canal where the nerve used to be, it just looks like it vanished.
And finally, in this little section, we have pulp stones. They are pretty much exactly what they sound like, tiny, round calcifications that form inside the pulp. On an X-ray, they look just like little pebbles. They don't really cause any problems or need treatment, but they're just another part of that tooth's hidden story.
Okay, for the deepest part of our journey, we're traveling all the way down to the very tip of the root, the apex. This is like command central for the body's response when a deep infection makes its way through the tooth and out into the jawbone.
So down at the root tip, dentists are basically looking for 2 kinds of clues: dark spots and light spots. A dark spot, or what they call radiolucent, means bone has been lost, usually because of an infection. A light spot, or radiopaque, means dense bone has been added. They're basically opposite reactions to the same problem.
Right, let's talk about those dark spots. You could be looking at a granuloma, which is just a mass of inflamed tissue. Or it could be a cyst, which is something that develops over a much longer time. Or it could be an abscess, that classic pocket of pus. The tricky part is they can all look like a similar dark circle on an X-ray, but they represent totally different stages of an infection. Figuring out which one it is, that's a huge part of the puzzle.
Okay, so we've covered the dark spots. What about the light spots? Well, the single most common one is a condition called condensing osteitis. This is actually the body playing defense. Instead of the bone dissolving away from an infection, the body responds to this chronic, low-grade irritation by building a wall, a fortress of dense, compact bone to try and contain the problem. It's a sign that your body is actively trying to protect itself.
So, after this whole journey, right, from the crown all the way down to the root, after seeing how teeth can break and move and literally change from the inside out, what's the one crucial thing to remember from all of this?
This right here is the whole point. An X-ray is an incredibly important clue, but it's only one piece of the diagnostic puzzle. That dark spot at the end of the root, it could be a granuloma, a cyst, or an abscess. To know for sure, a dentist has to combine what they see on the X-ray with a real clinical exam and your personal history. The shadow is a critical clue, but it's not the final answer.
And that really brings us to a much bigger idea, doesn't it? A simple dental X-ray can reveal this entire hidden world of trauma and defense and the changes of a lifetime. It just makes you wonder. What other amazing, complex stories are hiding just beneath the surface of all the things we think we know?